Electrostatics, point charges. We have a lot we need to talk about, and we'll start with Maxwell's equations for electrostatics and remind ourselves what approximations we had to make and what consequences the reduced set of Maxwell's equations has. We can make some statements already about electrostatics just by looking at Maxwell's equations. Given that, we want to go in and look at what the fields look like around a point charge, and we want to be able to quantify the field around a point charge. We'll then move on to point charges and talk about forces on charges. So we start with Maxwell's equations, and from our discussion in a previous lecture, for statics, nothing changes with time. So the time derivatives vanish and go to zero. And we saw when we did this that Maxwell's equations split into two sets of equations. One set will describe electrostatics, and the other set will describe magnetostatics. So we will proceed with this first set of equations describing electrostatics. The first of those equations that I listed was Faraday's law. And this states the curl of the electric field is zero. Remember, curl is the tendency of a field to circulate about some axis. So in electrostatics, Faraday's law is saying the electric field can't circulate about an axis. So it must form essentially straight lines, no loops. The second equation is Gauss's law. This says the divergence of the electric flux density D is equal to the charge density. This is telling us that if there's charge, the electric fields will either diverge from it or converge to it. So electric fields have to start and end on charges. The electric fields, again, are not allowed to form loops. That would be the case if the divergence was zero, if there's no charge. However, in electrostatics, there's no way to have an electric field if there's not charge. When we talk about waves, we can have an electric field without charge, but we're talking about statics. So electric fields start and stop on charges always. No charges, no electric field. And the last are constitutive relation. D is related to E through the permittivity, and in this case I'm drawing the permittivity as a tensor, but in this class we'll only treat that as a scalar quantity. But what we can point out here is that the electric fields no longer see the permeability. That's completely moved into the magnetostatic problem. So electric and magnetic fields have completely decoupled. I definitely want to talk about just visualizing the field around point charges, and I want to re-emphasize some points that I have made in earlier lectures. Let's start with a point charge. In this case, it's a positive charge, and I label that Q, Q being the total charge. Well, the electric field around that is a smooth and continuous phenomenon. It's not a discrete thing. So it looks kind of like a fog or a cloud just hovering around that charge. It is also a vector quantity. While it looks like a cloud or a fog, each point pushes in a specific direction. And in the case of a point charge, that push is away from positive charges, in the direction directly away from that charge. So here I'm visualizing the direction of the electric flux at randomish points throughout this cloud surrounding a point. Now, if I put my finger down here and I looked at the vector direction and just moved my finger a little bit in that direction, looked at the direction again, moved in that direction, and kept going, I would trace out what are called electric field lines. And they look like that. And so very often, you will see the field around a charge represented only with the lines. I really don't like doing this, and I would stress caution on this when you're just beginning, because this seems to imply that the electric field would exist on the line, but not off of the line. And that is completely false. The electric field is a smooth, continuous phenomenon. These electric field lines are really just a mathematical construction so that we can have some way of visualizing the field and keeping track of the direction of the field. But make no mistake, the field is not a discrete phenomenon. It is smooth and continuous, and these field lines don't really exist. They are a mathematical construction just to help us track the orientation of the field. So here on the left, that is the traditional way the field is drawn around charges. It's also easy to draw that. The picture on the right, I think, is less misleading. And that's the picture I recommend programming into your brain when you think of the field around the charge. However, we're going to draw the ones on the left simply because it's easier. And in 3 dimensions, it looks like this. And 3 dimensions is very hard to convey on a flat screen. I think really the only way to do that is to incorporate some kind of motion. So you'll see throughout this course, we're going to draw, when we need to, we'll draw 3D. Otherwise, we're going to try to draw everything in 2 dimensions as best as we can, but fundamentally, everything is a 3-dimensional problem. So these field lines are sticking straight out, and even in 3D, the field really is a smooth, continuous phenomenon. This is just our mathematical tool to help visualize the field. The direction of the field. Well, we have Gauss's law that says the divergence of the field is equal to the charge density. So that means if the divergence is positive, coming away from a point, that indicates positive charge. So the electric field lines from a positive charge extend outwards. Opposite to that, if we have a negative charge, the electric field lines converge on that. Sometimes the positive charges are called sources and the negative charges are called sinks. And the only thing wrong with that terminology is the sink can also, it also creates the fields. It's a source of the field. So sink and source are really just words telling us whether the fields are starting or ending there. But both charges produce the fields, just in opposite directions. If we have 2 charges at the same time, now we start to see a bit of bending of the fields. They're still essentially straight lines compared to loops, but now they're bent. We call this fringing. If one of the charges is a lot stronger than the other, that changes the way the fringing looks. Now let's get more mathematical. We have a good picture in our heads of what the fields around charges look like. Let's quantify this. So on this slide is the equation for the electric flux density around a point charge Q. And we're drawing it over to the right. So we start with a point charge. And there's a point out here that we want to observe the electric flux density D. This point is a distance, capital R, from the center of the point charge. And in doing this, what we'll need is a unit vector in the direction of R. So this is a unit vector in the direction from the charge to the observation point. And of course, it's a unit vector, so its magnitude is 1. Given all that, we can understand our equation. We see that the electric flux density is proportional to Q. So if we double the charge, the electric field also doubles in magnitude. We have a R squared in the denominator. So this means as we move away from that point charge, we're going to notice that the electric flux density gets weaker. And of course, it has a 1 over R squared relation. And then there's this unit vector here, and that's telling us that the electric flux density is pointing directly away from the center of that point charge. So that's how we quantify it. Now this is new. I just want to take a few minutes to do a very brief derivation of that equation. more just to show that that equation actually comes from Gauss's law. It's a consequence of Gauss's law, so it's not pulled out of thin air. So if we imagine a charge at the origin and we want to calculate the field around it, we apply Gauss's law to a point charge located at the origin. And so what we'll do is we'll set up a surface, a spherical surface. We'll integrate the electric flux around that surface, and that will give us the total charge. So we pick spherical coordinates. We write this double integral. We're integrating over theta and phi because we have a sphere, and that sphere is of radius r. And I put in the differential area in spherical coordinates. And due to symmetry, we know that the electric flux density will be pointed directly away from that point charge. So the D field only has an r component. We take the dot product, both or only r components, so the AR drops, and we just have our dr times everything else inside this parentheses. We then don't have a phi function, so we can isolate the integral of phi, and it turns out that will be 2 pi. And we can also bring some constants to the outside, and that is our d, the r component of d, and r squared, because neither of those are a function of theta and phi. Well, that integral over phi becomes 2 pi, and we bring that to the outside of the integral. Now we have an integral over theta, but there's a sine term in there. So the integral of sine is a negative cosine, and we bring that negative sign out here, and then we evaluate cosine of pi minus cosine of 0. And when we do that, cosine of pi gives us a negative 1, minus a positive 1 gives us a negative 2 inside these parentheses. That negative 2 combines with this negative 2 to give us a positive 4. Now we're in a position to actually solve for D. So this last final expression must equal the total charge Q. Solve that expression for the R component of D, and we have Q over 4 pi R squared. And then we can write that in vector form. The vector form of D is the magnitude that we just derived, and it's in the R direction. And so that's a derivation of the equation on the previous slide. It's a consequence of Gauss's law. So in fact, it's not really a new equation. Here's a good illustration of the 1 over r squared dependence. And we can think of this 2 different ways. In a traditional textbook, they would be looking at the density of the field lines. And if we don't change the number of field lines, as we move away, we can see that they're less dense. And that's a way that the field line picture of things can describe the overall intensity. But make no mistake, the electric field is a smooth, continuous phenomenon that we're seeing here is like a cloud. And the amplitude is decaying with a 1 over r squared dependence. So technically, it never goes to 0. But the reality is, if we move far enough away, we really no longer observe it. Another reminder of the direction of the field, it's diverging from positive charges, converging on negative charges, and these are the pictures that I think of when I'm thinking of the field. The lines just is too easy to confuse you with the field exists on the lines and not off of the lines, and that is a false statement. These are very good pictures, but they're also very difficult to draw. But these are the best pictures that I've come up with to visualize the field around charges. So charges the fields start at positive charges and end on negative charges. Now we're going to do calculations with this equation, and there's a different way to write it that I think makes the calculations a little bit easier, but is also a bit misleading. It's not incorrect, just it can be confusing. So over here we have our unit vector in the r direction and divided by r squared. And that was very simple, and we could look at the equation, we could see there's a 1 over r squared dependence, but it's maybe a little bit more abstract than we would like when we go to do a calculation. So instead, we'll describe the position of our charge with vector r sub q. And then the position where we're making the observation is just r. That means our unit vector AR is R minus R sub Q, and then we divide it by the magnitude of itself to get a unit vector. Now when we do that and we throw this expression in, we have R minus RQ, we have to divide R minus RQ by the magnitude cubed. Over here we had R squared, but here it's R cubed only because this numerator also carries information of the magnitude. We have to cancel this. And so that comes down to the denominator, and we do end up with an R cubed there. And looking at this, you could get confused and say, oh, there's a 1 over R cubed dependence, and that's not true. One of those gets canceled by the magnitude up here, and it is truly an R squared dependence. So in the end, I prefer this first expression for just loose thinking and understanding the dependence of R squared and the direction of things. And the second equation I prefer when I'm doing calculations. So just be cautious of that. Now we've expressed the field in terms of the electric flux density. We did that because the electric flux density is most closely associated with charge. But it may turn out that we want the electric field intensity, because the electric field intensity is more closely related to force. And so if we want to start calculating forces that charges put on each other, we will need to do that through the electric field intensity. So the way this works is we calculate the electric flux density, and then just in one simple step using the constitutive relation, we calculate the electric field intensity from the D field. So if we solve this equation for E, we can get a new equation to calculate the electric field intensity directly from the charge. I don't recommend doing that, although a lot of textbooks do this. A lot of textbooks will give an equation something like this. And there's a lot I don't like about that. First, it's implying that the electric field intensity is the more fundamental quantity around a charge, and that's absolutely not true. The other thing is this epsilon sitting here, and that leads to some ambiguity and confusion. So I look at that and I wonder, well, is that equation general? Does that equation account for if there's some kind of permittivity in the medium around the charge? But I don't see the epsilon r, so maybe that's a general equation. But the truth is there's actually an assumption built into that equation that it's in air. Well, what if it's not in air? Anyway, that equation is confusing, and all the textbooks give that equation. So in this class, we will calculate the electric flux density around the charge first. There is no permittivity in that equation, and it works always. And then when we need the electric field intensity, we just simply divide D by the permittivity, and we have the electric field intensity. So I'll get off my soapbox about that. Let's do an example. So let's calculate the electric field intensity at this point R due to a point charge over here, and this is in air. And here's the actual number. So we have a 2 microcoulomb charge, and that's a pretty realistic number. A lot of times examples in textbooks will say you have a charge of 3 coulombs, but it turns out the coulomb is a huge unit. So microcoulombs is much more realistic. And then, of course, we have our 2 positions. And so for right now, this could be meters, and I'm sort of, I guess, ignoring the units to keep the equations looking simple. And that's bad practice. We should carry units with that. So we want to calculate the electric field intensity, but we don't do that directly. We'll do this through the electric flux density D. And so here's the equation that we'll use, and this is the form that I think makes calculations easier, but is potentially a little bit misleading because it might make us think there's a 1 over R cubed dependence, and there's not. So the first thing I like to do is to calculate the R minus R cubed. And if I throw in the numbers there, I'll get this vector. So this is a vector that points from our charge to our observation point. Then I'll calculate the ratio of that vector divided by the magnitude cubed. Now when we cube the magnitude, we actually have 5 squared plus 2 squared, and then there's a square root here, which really raises it to the half power, and then we also cube it. So we sort of combine those, and it's to the 3/2 power. That might be a little weird why that's there, and now you see the answer and why that's there. So this new vector is this ratio. And now we can just plug that in our equation, and the math, I think, is easier. So the electric flux density, we plug in our numbers, is finally 50 in the x direction, 20 in the y direction, and I chose nanocoulomb per meter squared as my units. But we didn't want the electric flux density. The problem asked originally for the electric field intensity. So all we have to do is take our value for D that we found, divide by the permittivity, which is the free space permittivity times the relative permittivity. We said the problem is in air, so the relative permittivity is just 1.0. If we run the numbers, we get roughly 5.7 in the x direction, 2.3 in the y direction, and units are kilovolts per meter. We can draw that electric field. And notice it is in a direction. We have our charge towards R and continue. It's in exactly that direction. And that makes sense. So now we know everything about a single point charge. What about multiple point charges? So we look at the field due to a single charge. We look at the field due to two charges, and we see that there's this fringing. If we put in three charges, we get more fringing. And just for fun, let's put in a whole bunch of different charges with random positive, negative charges, and all kinds of craziness happens. So the question is, all right, we can visualize it. How do we calculate it? Here's multiple charges, two charges in 3 dimensions. And here we're visualizing the electric field lines, not to imply that the field exists on the lines and not off of the lines. It is a smooth cloud. These lines just help us track the orientation of the field. So it turns out, because everything is linear, the field obeys something called superposition. So if we have multiple charges, what we can do is calculate the electric field at our observation point due to each of those charges individually, and when we're done, add the results. So let's do this by example. Let's say we have 3 charges. So we have a charge 1, 2, and a 3, and at 3 different positions. And I would like to know what is the electric flux density at the origin. How do we solve this? Well, anytime we have a problem like this, I strongly recommend sketching the problem. Now, this is in 3 dimensions. I probably won't give you a problem on paper that you'd have to sketch in 3 dimensions, but we'll do it here just for the exercise. So we sketch it. We see that our observation point is at the origin, and we can see our point charges. And I color-coded it. The red is for the positive charges, and the blue is for the negative charge. And we can see where everything is. I even built in a little bit of an orbit, so the 3-dimensionality, we can help interpret that visually. We should now organize the problem and how we're going to solve this, because we have 3 charges. We have a bit of work to do. So using that concept of superposition, we know that the total electric flux density is simply the electric flux density calculated for each charge individually, as if those were the only charges that were there, and we add the result. So in other words, we'll calculate D1 as if the second and third charges don't exist at all. So it becomes an exercise like we just worked on. Then we move on and we pretend that the second charge is the only one there. And we calculate the D field that results from that. Then we move on and pretend that the third charge is the only one there. And of course, we'll have 3 answers. We add them all together, and then we'll have the total D field that we would see at the observation point due to those 3 charges. So we calculate D1, and our sketch over to the right has changed a little bit. I'm visualizing the electric field lines emerging from the first charge, and also visualizing the direction of D1, which should be in a direction coming immediately from Q1 through our observation point. So this is the equation we'll use to calculate D1. So this is just an exercise from our previous section where we talked about single point charges. I'll calculate that difference, r minus r q1. So this is a vector pointing from q1 to our observation point. Then we'll calculate that ratio of that r vector divided by the r vector cubed. We get a number for that. And then we can plug in all of our numbers and get our final answer for D1. This is the electric flux density at our observation point, and the units are coulombs per meter squared. And you'll notice I got a little bit lazy and wasn't using the units in the intermediate calculations. And well, that actually wasn't due to laziness. If I put in the units everywhere, my equations grow and cover the picture. And anyway, I ended up here. So I put the units in at the end, but we should be carrying units through every step of the calculation. So we have D1. We'll repeat the exact same thing for D2. So now we'll pretend that the only charge that exists is that second charge. And while I'm drawing those field lines with arrows as if they're emerging from Q2, I drew them being blue, so they're actually negative. So the actual direction is toward Q2. So rather than turn the arrows around, which I think would have made the picture a little bit more confusing, I just drew the lines as blue. But make no mistake, those field lines are pointed toward Q2. So we have our general equation for D2. We'll calculate R minus RQ. Then we calculate that vector ratio. Then we plug in our numbers and we get D2. And here are the units that I should have been carrying through all of the calculations. And we do it over again for D3. You can see the pattern here. If we had 5 charges, we would be doing this 5 different times. We write our general equation. We'll calculate the R minus RQ. We then calculate that vector ratio of R minus RQ divided by the magnitude of that cubed. Once we have that, we then plug it into our equation for D3, and we end up with our answer for D3. And here's also our units that we should have been carrying through every step of the calculation. So we have D1, D2, and D3, each individually, just pretending that those charges alone were the only charge that was there, and we got 3 separate answers. Now we need to bring these together, because in reality, all of those charges are sourcing or sinking fields. Each one produces an electric flux density at our observation point, and we add them together to get the overall total electric flux density at our observation point. So we add up our answers, and that's what we get, units of coulombs per meter squared. And in my final answer, I would probably adopt a more sophisticated notation. And that's our final answer for the electric flux density. Now, had I asked for the electric field intensity, we would have done everything right up to this point. I would just now divide this by the permittivity to get the electric field intensity. So that's how we do multiple point charges. It's just an exercise where we do a single point charge for each of our point charges and add up all of the answers. Now let's think about forces on these charges. Suppose we have an electric field. And suppose we have a positive charge somewhere in the middle of that electric field. That electric field will put a force on that point charge. And if it's of a positive charge, the force will be in the same direction as the electric field. Now, unfortunately, this equation does not come from Maxwell's equations. This comes from something called the Lorentz force equation. I did mention it in an earlier lecture, and in fact, that Lorentz force equation has to go along with Maxwell's equations to have a complete set of equations describing classical electromagnetics. So unfortunately, this one does not come from Maxwell's equations. Now let's say we have a negative charge. Well, the electric field will put the same force on that charge except now the force is in the opposite direction of the electric field simply because the sign of the charge is negative. So overall, our final equation for this is force is charge times the electric field. And in this case, the force has units of newtons. So as an example, suppose there's an electron between two metal plates. The metal plates are separated by 1 centimeter. We apply 10 volts, and this is in a vacuum, but there happens to be one electron floating somewhere between those plates. What force does that voltage put on that electron? So the first thing is to sketch the problem. In this case, we have our two parallel plates, so a top plate, a bottom plate. We are applying 10 volts to those plates. Here's our electron. The plates are separated by 1 centimeter. And when we apply a voltage, that establishes an electric field between those plates. In fact, it establishes a uniform electric field. So the electric field between the plates, and this is something we'll actually talk about later, but for now, the electric field is voltage divided by the separation between the plates. So it's 10 volts divided by the separation of 0.01 meters or 1 centimeter. And we end up with an electric field of 100 volts per meter. Now that we have the electric field intensity, now we can calculate the force on that electron because we know the charge of an electron. So force is charge times the electric field. The charge of an electron is negative 1.60, and there's more decimal points that I'm not putting here, but there's more decimal points here. So negative 1.6 times 10 to the minus 19 coulombs times the electric field, which we calculated to be 100 volts per meter. If we run the math, we get minus 1.6 times 10 to the minus 17 newtons. It turns out that's about minus 16 attonewtons. That's a very, 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 very small number. I can barely comprehend how small that number is. And that's simply because the charge of an electron is so small. But that's interesting to know. This brings us to Coulomb's law. Coulomb's law calculates the force that one charge will put on another. So we start off with two charges. We have a first charge at position R1 and a second charge at position R2. Well, the second charge, both charges have electric fields, but conceptually we'll focus on the second charge. This has an electric flux density around it. And if we're thinking about this just as a single charge, we're now experts in calculating that electric flux density that exists around that charge. So we have that. From there, because we're interested in force, now we need the electric field intensity. So we have to consider the permittivity that this is in. So given the electric flux density due to that second charge, we divide by the permittivity, and that now gives us the electric field intensity around that charge. Now that we have the electric field intensity, we can now apply that to the first charge and figure out what the force is now that we know the electric field. So the force on the first charge due to the second charge is Q1 times the electric field intensity produced by the second charge. So we look at the distance between those charges. We'll write that as R12. We can also define a unit vector that's pointing from the first charge to the second charge. And if we plug in all of this stuff, here's our final equation for that force. And it has the product of the two charges divided by 4 pi epsilon r. Now we have to have an epsilon here. And we can also write it in this other form that makes calculations a little bit more convenient. But make no mistake, there is a 1 over r squared dependence for the force. And over here it could look, if you're looking quickly, that there's a 1 over r cubed dependence, but that is definitely not true. So this tells us the farther apart those charges are, the weaker the force will be. If we make the charges larger, we'll make the force larger. There's also the permittivity here. And notice as the permittivity gets larger, the force will actually get weaker. So qualitatively, we can sort of wave our hands and explain that. If we have a highly permeable material, the electric field is going into polarizing the material instead of putting a force on that other charge. So think of it that way. There's more work for that second charge to do, or there's more work for the field to do from that second charge when there's a high permittivity medium. So that is Coulomb's law. It's just talking about the force that one charge puts on another. The direction of that force is always along the line extending immediately from one charge to the other. The force is directly proportional to the product of the charges, so if either charge becomes bigger or smaller, the overall force will become bigger or smaller. The force is inversely proportional to 1 over r squared. That's not a real surprise. We keep seeing that in all of our equations. I'll also mention this is electrostatics. The charges have to be stationary for these equations to be valid. As soon as something moves, things are time changing, and we very likely have to take into account electrodynamics. And now suddenly there's a magnetic field there, and our analysis gets very complicated very quickly. Let's do another example. What is the attractive force between the electron and proton in a hydrogen atom? So here's the solution. We'll always start off by sketching the problem. So a real simple sketch of an atom: we have a nucleus with a positive charge, we have an electron with a negative charge, and there's some radius separating those two. Well, we know the charge of the electron and proton. They have the same charge, just opposite sign. And I went on the internet and I looked up the radius of a hydrogen atom, and it was about 53 picometers. So that's close enough for us. Let's calculate the force. We have our force equation. Let's just throw in these numbers. So of course at the atomic scale there's not really going to be a permittivity, so the relative permittivity is just 1, and this r squared is our 53 picometers. And if we do the math, we get around -8 times 10 to the 8 newtons, and this comes out to be 82 nanonewtons. Now that actually surprised me how large that number is, but these are tiny, tiny particles. So tiny, tiny force. Now let's think about the force on a particle due to multiple charges. So in this case, we would like to calculate the overall force put on Q0 due to the surrounding charges. So each of those charges will individually put a force on Q0. And of course, the overall force is just the sum of those. So we have our superposition again. So we look at this one at a time. The first charge has an electric field around it. We jumped immediately to the electric field intensity. That electric field then puts a force on Q0, and that force is in a direction immediately along one of the electric field lines. So it's oriented in the direction along the line connecting these two charges. So we'll call that F01, meaning the force on charge 0 due to charge 1. Now we move to charge 2. In this case, it's a negative charge, so the electric field lines are actually converging onto Q2. And so the force, since Q0 is a positive charge, the force is in the direction of the electric field, and of course along one of those lines. Now we move on to the third charge. In this case, the electric fields are diverging from the third charge, and here's the force, F03, and of course it's along one of those field lines. And then we move on to the fourth charge. It's a negative charge, so the fields are converging on it. And so that puts the force in a direction connecting Q0 toward Q4. We write that as F04. So we walked around this problem. We looked at each charge as if it were the only charge and calculated the force that that charge would put on Q0. Now our job is to simply add all of them. So we look at all of the forces, each one due to the individual charges, and add them up to get the overall force. And in this case, the overall force is almost straight down. So if we were to suddenly turn time back on, that Q0 would initially move in the direction of F0. Now, as soon as it moves, the electric fields around it now look different and the direction changes. And this is a problem that we'll actually solve later on. But for now, we're just calculating the overall force, and it obeyed superposition.